start also. Okay, so thank you everyone for joining us for the spring semester of the Joint Israeli Probability Seminar. Today we're very happy to kickstart the semester with Gal Kronenberg from the University of Oxford to tell us about independent sets in random subgraphs of the hypercube. Thank you, Gal.
Hi, thank you, Ron, and thank you very much for the invitation. It's a great pleasure to give a talk here. As Ron mentioned, I'll talk about independent sets in random graphs of the hypercube, and this is joint work with Inon Spinka. Okay, so as you can imagine, the main topic of this talk will be independent sets, which are sets of vertices in graph that contains no edges. So we are not taking two vertices that are adjacent in our graph. And this has strong connections, as some of you might know, to the hardcore model from statistical physics. So I'll also mention some things about that. And in the second part of the talk, I'll also show connections to some antiferromagnetic Ising model that somehow comes up in our proofs. Okay, so when thinking about independent sets, we may ask several problems, and one example is a counting question. So how many independent sets do we have in our graphs? If we go one step forward, we can think about weighted counting, which is just another way of saying the partition function of the hardcore model. We can also consider more structural questions. So how does a typical independent set looks like if there is a long range order or disorder, and so on. I'll mainly focus on the first item in this talk, but I'll also try to mention some things from the second one. I'll just want you to keep in mind that I'll mainly focus on, I'll mainly consider independent sets, but you can keep in mind, for those of you who are interested in the hardcore model, that everything I say also works for the hardcore model similarly. Okay, so let me start with some motivation. I will try to motivate the problem both from the statistical physics point of view and the combinatorial point of view, which is a bit more natural to me because I'm coming from combinatorics. So, but let me start with the hardcore model with the statistical physics point of view. So, yeah, I don't know if all of you are familiar with the hardcore model, so let me just give some insights there. So so this is just a model of gas. So we want to think about particles of gas in some room, and we want to focus on one small box and see what's going on there. And we want the particles to not overlap. So we don't want to allow them to be in the same place. And then we want to study its behavior, and one way to do it is just to discretize our room. So for example, now I just make it the grid, and I let the particles be on the vertices of this graph. And the fact that they don't overlap just means that I don't want to allow two particles to be on vertices that are adjacent to each other. So what we get is exactly an independent set. An independent set in our graph. Okay, so we can have we can see it. We can have many examples, but this is just an independent set in our graph. We don't have any edges between them. Okay, so this is the motivation for the hardcore model.
Why hardcore? Why the word hardcore?
You can ask the specialist here, but
it's just convention. It doesn't reflect.
No, it means that they are strictly not allowed to interlap. Unlike software core where they are allowed to overlap, but there is some penalty for that.
It's okay, like you have a physical particle whose core is hard, so they cannot push each other. That's the idea.
Okay, so we see we have very nice explanations here. Thank you. Okay, so we usually think of this model with some fugacity parameter lambda. So for example, the probability, okay, so according to this model, so the probability to sample one independent set, we want it to depend on the size of the set with this fugacity parameter lambda, and we want to normalize it with this function, which we call the partition function of the graph. So the partition function of the graph will just look like this. This is just the normalization function, and yeah, and it's easy to see that if we just take lambda equals 1, then this is just a count. Okay, so we can look at this as somehow a weighted counting of independent sets. And if we take lambda equals 1, it's easy to see that we just get the total number of independent sets. So counting the total number of independent sets is just a special case of the partition function of the hardcore model. So this is the connection in general. Okay, so now that we have this, let's start with some very simple examples. So the first example is very, very simple. I want to consider the complete bipartite graph, KDD. So we have, it's a bipartite graph, so we have two sides and all the edges between because it's complete. And I want to start by counting the independent sets here, which is a very easy task. So of course, every side is an independent set itself. So all the subsets here are independent. So the number of independent sets on each side is 2 to the d, and these are the only possible independent sets because I cannot take an independent set which will intersect with both sides because we have all the edges between them. So these are all the possible independent sets. So I have 2 times 2 to the d minus 1 because I don't want to count the empty set twice. Okay, so these are the total number of independent sets here. So let me just add this notation. I of G will be the total number of independent sets in G. And I just want to write it in terms of the number of vertices to be able to compare later. So this is how it looks if I write it in terms of the number of vertices of our graph. Okay, now let's move to the next simple example. Instead of one copy of the complete bipartite graph, I want to take several disjoint copies of this complete bipartite graph and count the number of independent sets here. So of course, there is no interaction between these parts, so no edges between them. So it just means that the total number of independent sets will be the total number of, in one of them, to the power of k, right? If we have k copies. So this was also easy to calculate. And yes, and we want to write it once again in terms of the total number of vertices to compare later. Okay, so a very interesting, nice conjecture was made by Alon in 91, say that in some sense this is best possible. So he conjectured that for every deregular graph, not necessarily bipartite, the total number of independent sets is maximized by this example. So with at most what we get here, we cannot get something more. So he showed some approximated version of this theorem and of this conjecture, and later it was proved by Kahn for the bipartite case and by Zhao for the other cases. So now this conjecture is settled. But I do want to spend one slide talking a little bit about the proof of Kahn, and the reason is that he's using, in his proof, he's using some entropy methods to show discounting, to show the total number of independent, to bound the total number of independent sets. And his method was later used by, in this type of questions by many other authors, including us. So some of our ideas are coming from that. So of course, we need a bit more, but this is the base idea. So let me perhaps sketch the proof. So for this, I'll recall the definition of entropy. So if I have a random variable, sorry, discrete random variable, I'm talking only about discrete random variables here. The entropy of X will just be this sum, where the sum range over all possible values of X. And the connection, we can see a connection between the entropy of a random variable and some counting argument, which comes from when we apply Jensen inequality, so this function is concave, and we get that the entropy of X is at most the log of the number of possible values of X that get positive, that you get with positive probability. And we have equality here when X is uniformly chosen. So this will be useful for us, and let's see one simple example just to proof by example. These are my favorite proofs. Okay, so let's take a uniform independent set from some graph G, because we're talking about independent sets here, and this will be the entropy, and of course the probability, because it's uniform, will be 1 over the total number of independent sets, and this will just be, if we look at this expression, this is just the log of the total number of independent sets. So here we can really see a connection. We have a uniform chosen independent set, and we can really see the connection between entropy and counting problems. Okay, so now we are ready to prove the theorem of Kahn. What do we want to prove? We want to show that in every d-regular graph, bipartite graph, we proved it for bipartite graphs, the total number of independent sets is bounded by what we saw in the previous example. So how do we show it? So let's take a uniform independent set, because this is this will be the easiest choice. And I want to think about independent set as a 0, 1 vector. So 0 if the vertex is not in the independent set, and 1 if it is. So independent set of a bipartite graph on set of vertices V1 and V1, V2. These are the parts. And now I'll just list some simple properties of entropy. If you know them, if you're familiar with them, great. If not, then you will have to believe me, but they are also very easy to verify, or at least most of them. So we know that there is some chain rule, so we can write the entropy of X using the chain rule. So just the entropy on the vertices on one part, and then on the other part condition on the first part. So this is just another way to write the entropy of X. And then we want to bound both of these elements. So let's start with this one. So we will just use subadditivity. It's known that the entropy is subadditive. So instead of writing it like this, we want to write it as a sum vertex by vertex. So this will be the first thing, but unfortunately subadditivity will not be good enough to bound this part, so we will need something a bit stronger. And for this, we use the famous Schur's lemma that tells us that instead of taking, so in this special case, it will tell us that instead of summing over each vector separately, we can somehow average around the neighborhood using the fact that our graph is d-regular, bipartite and d-regular. Okay, and that's basically it. So we can write the entropy of X as we can bound the entropy of X by this sum, but the expression that we have here inside the sum, so it's just exactly the entropy of a uniformly chosen independent set from KDD, because we have D time the vertex and this. So this is exactly what I have here, and we just showed before that this is the log of the total number of independent sets, which was shown before to be in the previous slide to be this expression. So this is on one hand. On the other hand, X is uniformly chosen. So once again, using this observation, we get this connection from the other side, and that's it. That's the proof. So it's a very nice idea that was later used in many works. Okay, so now we have really good bound, like the best bound possible, for if we want to consider any d-regular bipartite graph for the total number of independent sets. And perhaps the next step will be to try to see what we can get for graphs that we know a little bit more about their structure. Perhaps one, or maybe the most.
Can I ask one quick question?
Yeah.
If you replace d-regularity by minimum degree d, should one expect a similar result, or should one not expect a similar result?
Minimum degree D. Similar result in what sense? So,
well, sort of the same, some kind of bound like that.
If it's also maximize it. I am not sure. I have to think about it.
Okay.
You can
Yeah.
probably then take one side to be huge, right? And then
Yeah.
have a huge independent set. So
Yeah.
many more independent sets, I think.
Okay. Yeah.
Yeah,
thanks.
I don't think. Yeah. Sorry. Okay. So now we want to have a look at a graph with a bit more that we know a bit more about its structure, and a natural or first candidate would be the hypercube, which is the main object in this talk. So we want to consider the dimensional hypercube. So QD will be the dimensional hypercube, and once again, an independent set will just be a set of vertices that contain no edges. So we don't have, in this set, we don't have vertices that were adjacent in this graph. So this is an example. Okay, so this is not the hypercube, it's the grid, but it's easier to draw. So I'll just, for the illustrations, I will use this. Okay, so this is an independent set, and once again, IQD will be the total number of independent sets. And if we want to think about the partition function, let me just recall the definition. So if we want to look for general lambda, so the partition function of the hardcore model is just this weighted counting. Okay, and one question we can ask is about the value of this total number of independent sets. So we want to compute it, and we want to think of D being large, so as D tending to infinity. Okay. Okay, so apparently this problem has a lot of history, but before I'll mention some results, let us just look on some trivial bounds that we can get, and also ones that are not so trivial. So let's start with showing some trivial upper and lower bounds. So the upper bound for the total number of independent sets, okay, we can just bound it by the total number of subsets in our graph. So in the hypercube, we have 2 to the d vertices, and this is just the total number of sets. Of course, it's an upper bound. For the lower bound, so we know that the hypercube is a bipartite graph, and it's deregular. So we call the sides sometimes even and odd. I will also refer to them as even and odd in this talk. And each side contains 2 to the d minus 1 vertices. So we can do a similar calculation as we did before. So we can start by considering only subsets that are inside one of the sides of the bipartite graph. And of course, this is independent. These are independent sets because it's a bipartite graph. So it will give us, once again, exactly as the calculations that we did before, that in each side we have 2 to the d minus 1 independent sets, and this will be a lower bound of the total number of independent sets, because we want to consider sets that are only on one side. Let me just mention before, in the first example, we had the complete bipartite graph. So we couldn't take independent sets that intersect with both sides because it's complete, but the hypercube is not complete. So now we do have some independent sets that intersect with both sides, but we didn't consider them for the lower bound because we just wanted to calculate a very easy and trivial lower bound. But this is not best possible. Clearly, we can have more options in this case. Okay, so so we have 2 bounds, upper and lower. They're pretty far from each other. We want to try to improve them. So let's start by improving the upper bound. We have the result of Kahn, which is true for every deregular bipartite graph, and also for the hypercube. So we're using the result of Kahn, and we get something better than the upper bound. It looks more similar to the lower bound, but still quite far. I just remind you that D is tending to infinity. So this is, there is still a big gap here. Okay, so now let's try to improve the lower bound. And as I mentioned, we do have, in this case, independent sets that intersect with both sides. So let's start by considering those independent sets that have a small part on one side and the majority on the other side. So we want to take like a small part from from one side. So we just want to choose it, and once we chose it, so now we forbid all the vertices from the other side that are neighbors, right? So we forbid the entire neighborhood, and this neighborhood is of size at most dk. So this is what we get here. And of course, we have some double counting here, but this is very negligible. So this will give us a lower bound. And this lower bound is very similar to the trivial lower bound that we had before, but we still get another factor here of square root of e. So we were able to improve it, but only slightly. And of course, we may ask, okay, so why should we take unbounded? Maybe we can take it to slowly tend to infinity, and this will also be negligible. So the calculation will be similar. So it will give us something much better. Okay, so now we have new upper and lower bounds, and the question is which one is closer to the truth? Okay, so very surprisingly, perhaps, it was shown that the truth is in the lower bound. So a very classical result of Korshunov and Sapushenko from the 80s tells us that the total number of independent sets is approximately what we get in the lower bound. So 2 times square root of e, 2 to the 2 to the d minus 1. And besides it being a very nice result itself, it also hints us, or intuitively we can see that, okay, so how do we got the lower bound? Before we considered only independent sets that has only small part on one side and the majority was on the other side. So it's also intuitively, at least, giving some intuition that most of the independent sets have this structure in some sense, that the majority of them are on one side and only a small part is on the other side. And this is like already giving us some, so they already gave some structural information about these independent sets. And the result was generalized by Galvin for the hardcore model. So he gave results for several values of lambda. I just wrote here the most general one. So when lambda is at least log d divided by d to the 1/3, then the partition function is given by this formula, and you can just see that if you plug in lambda equals 1, you get exactly the formula of Korshunov and Sapushenko. So this is just a generalization for other values of lambda. Okay, so next we want to see if we can improve this little O of 1 term. Maybe we can give a more accurate result here. And this was done very recently by Jensen and Perkins, who gave a formula and an algorithm to calculate this little O of 1 term. So I just wrote the first expression here, but you can calculate as many as you wish. And they also gave it to, okay, and they also did the same thing for the general hardcore model. I just mentioned here the case that lambda equals 1, but this is this will generalize for all the relevant lambdas, also from the result of Galvin. So this little of 1 term, they can give a lot of information about it. And perhaps from results that I want to mention, so they're not on the hypercube, but on a closely related graph. So the Tori and ZD, there were recently several results that given for these graphs by others, that some of them are Lyonians. So I just wanted to mention these two because these are all also related to this type of problems. Okay. So now that this problem is, that we know the history of this problem, so let's move to the random setting. So in this talk, I will consider the graph, the random graph QDP, which is a random subgraph of the hypercube. So we keep each edge independently with probability P. So we delete each edge independently with probability 1 minus P. And I want to consider a similar problem, so I want to understand the value of this this parameter, so the total number of independent sets in the graph QDP for a large range of P, and also when D is tending to infinity. So this will be the goal here. So let's just see another small drawing. So as you just the differences between the for the previous problems. So now perhaps there were vertices that were previously neighbors in QD, but now in QDP, there is some probability that these edges will be erased. So possibly they can be in the same independent set. So of course, the count of independent set will be, so there will be more independent sets in, it's likely that we will have more independent sets in this case. So this random graph was studied for also for other type of problems, and it's known to have interesting phase and transitions. So let me just mention two of them. So it's known that around 1/2 QDP, this graph has the threshold for, it's the threshold for connectivity, for perfect matching, and very recently it was also shown to be the threshold for Hamiltonicity, which was open for a long time. Another interesting point will be around 1/D, which is known to be the threshold for a giant component. This was also studied by many others. And in this talk, perhaps I would like to suggest other interesting point to consider, that, I don't know, maybe something interesting is happening around them. Okay, so let's start stating the results. So the first result will be, okay, so if we, the most general one perhaps, so if P is at least some constant log D over D to the 1/3, then we start by calculating the expectation of the total number of independent sets. So we have that the expected number of independent sets is given by this formula. And you can see that if we take P equals 1, which will just give us QD, we get exactly the result of Korshunov and Sopchenko. And similar to Jensen and Perkins, we can also give a very accurate information about this little of one term. So I just once again wrote the first term to give you an idea, but this can also be calculated for any accuracy that that we want. Okay, and okay, so if we can also calculate higher moments and not only the expectation of this total number. So we also have the formula for the higher moments for the total number of independent sets. And once again, this little of one term here can be done much more accurate. I will not write it here because it's too long for the presentation. Okay, so now that we have the moments, before moving to more results that we can obtain from it, let's see one example just to have an idea how it looks like.
Sorry, what is A of P?
It just, yeah, it's just a function. I didn't want to write it here, so it's just a function that depends only on P.
Okay, thanks.
Some polynomial function of P. Yeah, I didn't want to specify it here, sorry. It's just not very nice. Okay, so for P equals, okay, so let's just see what it gives us. One example, so for example, for P equals 1/2, we can get a very, yeah, a very closed form for the expectation, for example, and for the variance. And you can just plug in the numbers and calculate them and get something that looks like this. Once again, this little of one term can be calculated. Yeah. Okay, so now that we have the moments, first we want to ask if we can say something about the distribution. And yes, so the answer is yes, we can for some values of P, not for all of them. So when P is tending to 1, perhaps but not too fast, then we know that this centralized variable is actually normally distributed. So we have some information about the distribution when P for large values of P. And if we want to consider smaller values of P, then we know that
this limit is D is changing as well. What's the story? I mean, QD is for fixed D. It's a discrete thing.
For fixed D, so we want to think of D as tending to infinity, right?
So D, yeah. So D and P are both. P's going to 1 and D's going to infinity, and there's some bound on how fast P is going to 1 in terms of D, right?
Yeah.
Okay.
Yeah. Yes. Okay. Maybe I should have written it more specifically. Oh, I see there is. Oh, yeah. Yeah, P is function of D. Sorry. Someone asked in the chat. Now I need to find out how I close the chat. Oh, this Mac. I don't know how to do it. Oh, sorry. Okay. Okay. So now let's look at slightly smaller P. If we can also get something here. So when P is at least 2/3, which is interesting why it's 2/3, then we can get some information. So we know that this expression is tight, but it's not converges to 0. So let's see what this gives us for the value of the total number of independent sets. So we can write it like this, and this okay, but here we have some bound. So we know that, so this theta is, okay, I don't want to get into it, but it's with high probability big O and with positive probability omega. But the important thing, or maybe the interesting thing, is that it shows that there is the 2/3 is a point where we have a non-concentration. So there is no concentration for P equals 2/3. But if we do want to get some concentration, so we can go a bit above P, above 2/3, and get concentration results. So with high probability, the total number of independent sets will be given by this expression. And once again, the level of 1 here can be more accurate, and you can see that this 1 plus level of 1 term is in the main term and not in the exponent here. So it gives really a concentration result there. So perhaps, so we can really see that around 2/3, something is changing, at least in the moments. So these are all, okay, these are all corollaries of the theorem about the moments, and we can see that there is something going on there. Okay, so I see that, oh. Okay, I see that there are many questions, but I don't know. In the second, okay, I don't understand if these are questions or discussion.
It has been answered regarding whether P and D are functions of each other, and D is tending to infinity. D is always tending to infinity when you write the little o of 1 and so on. This is always the D going to infinity limit. I guess in the second corollary, you also ask P to be bounded away from 2/3 in a certain way. And in the first corollary, P goes to 1 as D tends to infinity.
Yeah.
They go simultaneously. Yeah. Thank you.
Okay. Okay, so maybe if there aren't any questions, maybe I will also mention, something about the law. If we talked about the bounds of P, so maybe I'll also mention something about the lower bound. So clearly, if P is too small, then the behavior will be different. For example, if P is little of 1 over D, little of 1 over D, then 1 over D is the threshold for giant components, so everything will look different. So of course, some lower bound on P is necessary, but we don't have a phase transition result here. So we we don't know what happens below it, but this is coming from the method. So I don't know if you remember, but you could also in the result of Galvin, we got a very similar lower bound on lambda. So this kind of lower bounds are somehow a restriction of the methods that people usually use in this type of problems. And yeah, so some lower bound is necessary, but probably this is not the where the phase transition occurs. So probably it's smaller. Okay. 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 So now, in the rest of the time, let me say a few things about the proof. So let me start by just mentioning the methods, the main method that we're using, and then I'll talk a little bit about each one. So the first observation that we use is that we show some connection between this number of independent sets in QDP and another model that can be seen as a positive temperature model. And by analyzing this model, we will get information about the moments of our model. So I will talk about it in the next slide. And we also used some cluster expansion of Polymer models that was used also by Jensen and Perkins. We also need some approximations or containers that goes back in the proof already by, it was used already by Khrushchev and Saposhenko in their proof and by many others after. And the fact that we have, that we look on a random subgraph, from this fact, we also need another tool, which is, this is where we use the entropy methods that I mentioned before in a bit more general way. Okay, so let me start with showing the connection to this other model. So, okay, so assume that we have any graph G, not necessarily QD, so we have any graph, and we want to look at a random subgraph of it. So GP will just be the subgraph where we keep each edge independently with probability P. And we want to look at an expected number of independent sets in this graph. So this will just be the sum of probabilities, but each edge is deleted with probability 1 minus p, so we just get this sum. And by writing the parameters a bit differently, so let's do some parameterization, we can write this sum like this. And this is and this can be viewed as a partition function of some different model. So let's define this model. I will define it for general lambda. So ZG lambda beta will be the partition function of this model given by this formula. So the probability to sample one set, this time this set doesn't need to be independent. It's allowed to have edges in it. So the probability will be this expression divided by the partition function, of course. So this is a different model. And you can see that, okay, so we go over all subset, not only independent, but if we have edges inside of our set, we're allowed to have edges, but it's coming with some cost. Okay, so if we have many edges, of course, it will look different than if we have a small number of edges. So we want it to be weighted in somehow according to the number of edges. And intuitively, it's a bit similar to what's happened in GP, like the random subgraph, because there might be two vertices that previously were neighbors, but now with some probability they are not neighbors. So this is in some sense the cost that we're talking about. But in this, now that we're thinking about this model, we don't think about random subgraph and we don't think about independent sets. We just think about sets and the fact that they have edges between them is coming with a cost. And as I mentioned, it can be seen as an anti-ferromagnetic Ising model. So I'm using this writing, but quite easily by changing of parameter, you can write it in the more usual way to write an anti-ferromagnetic Ising model. But as I mentioned, for me, I'm coming from the combinatorics. For me, it's more natural to look at it as weighted counting, but it's the same. It's just the same. Okay. So, and another thing to know that if beta is tending to infinity, then we just get p equals 1, and this is just the model G, and this is just the graph G. So when beta is tending to infinity, we just get the normal partition function of this graph. And when I talk about partition function of the hardcore model, we can, or of this model, of course, we can always take lambda equals 1. And then the counting is not weighted, at least not by the size of the set. Okay, so let's just summarize. So here I showed you for lambda equals 1, but of course I can do it for every lambda. It's just a little bit longer, not much. So we know that the expectation of the partition function of the random graph is just the partition function of another graph in another model. Okay, so given this observation, we now want to study this partition function, this weighted sum, but this sum is huge, and understanding it is not a trivial task. So how do we do this? We want to do perhaps, or want to show perhaps something similar to what people did in the hypercube. So we want to understand what is the main, where is the main contribution comes in this, where is it coming from, the main contribution in this sum. And similar to the other works, we also want to show that also in this case, we have this property that most independent sets, or a typical independent set, has this property that the majority, not independent set, sorry, set, that the majority in some sense, because we have some weighting here, the majority of the set is on one side, and on the other side, there is only a small bit of the set. So this is basically what we want to show, that, okay, so E will be for the even side, and O will be for the odd side in the hypercube, and we want to show that either most of the independent sets lies on the even side, or it lies on the odd side. So the cases where both are big is the case that both are big is not really happening. Okay. Okay, so now we have this huge sum that we want to deal with. Okay, so I went back to lambda equals 1 just because it's easier and nicer to write, but once again, you can think about it for general lambda. Okay, so now we have this huge sum that we want to understand, and instead of summing, so if we want to show that it's indeed like the main part is coming, the main contribution is coming from this set. So instead of summing over all sets, I just want to change the summation, and I somehow want to sum over the part that it's not in the main side in some sense. So eventually I would like, so now I just wanted to write it as equality, but eventually I would like to think of A being small, like being the local deviations from the, what we call the ground state. Okay, but I just wanted to do like a change of summation here, and instead of summing over all sets I want to sum over the different parts. And this 2 to the minus 1, of course, is coming from the easy part, the good part that doesn't have edges in it. Okay, so we have still we have this huge sum that we need to understand. And just maybe to give you some intuition about how it relates or differs from the previous works. So okay, so assume that we have this bipartite graph. We are in the hypercube, and we have a small set in the wrong side or in the other side. We call it A. Sometimes we call it a defect. And now we will look at its neighborhood. So in the original hardcore model, when you think about the hardcore model in QD, then we know that there aren't any edges between them. So if we want this set to be in our independent set, it means that we forbid all of this. So in some sense, this is the cost. This reflects in the cost. The weight of A will have this weight. So the weight of A is pretty easy to understand, and the difficult part, it will be to understand the sum of the weights and bound them, because we somehow want to bound them and to understand them. However, in our model, in this what we call positive temperature model, then we do have edges between these sets. So already when we want to think about the weight of this one set A, this is already a much more complicated task. So we already have we want to look at the subsets of this set and we want to take them into account because they have different weighting. So this is already much more complicated. So even summing, before even thinking about the whole sum, so even bounding this thing, it's already a non-trivial task. So let's see how we can deal with it. Okay, so this is again what's written before. Yes, so if we write this partition function like I wrote before, then okay, so this was the weight as I defined before, and I want the and this is very difficult to calculate, as I mentioned. So I somehow want to split this sum. So the way to do it, or one way to do it, will be to split A somehow into subsets, but I want this weight, or the way that I split it, to have this property that I can write it as like this, as a multiple of the weights of several sets. So this will happen if I will take this, if I'll split A to its so-called two-link component. So two-link is just I wouldn't say it's a connected subgraph, but it's a two connected subgraph. So because it's on one side, so it cannot be connected, but I want it to be of distance too. And this is the intuition behind the definition of a polymer. So this is exactly how we want to think about a polymer. So let me write the definition of a polymer. So a polymer A is a subset that contains in one side of the hypercube. We have some restriction on the size of A. This restriction, okay, so of course, intuitively, it's coming from the fact that we want to think of A being small because this is the defect side. We want to think about it as the defect side, but it's also like technical. It also has some technical reasoning. We want to use some expansion properties of the hypercube, so we have to limit the size of A. But the constant here, it's 3/4. It's just, it can be any other constant which is strictly larger than half but smaller than 1. So 3/4. It's just, you can choose anything else, almost anything else. Okay, so we have some restriction on the size of A, and we want A to be two-link. So we wanted to have its vertices somehow, the two connected graph, the two graph to be connected in some sense. Okay, and then we get that that every subset. Okay, now A. Maybe this is confusing. Now A is just a subset; it's not a polymer anymore. So any subset can be, due to these properties, can be written. The weight of every subset can be that is contained on one side can be written as a multiplicity of its polymers, of the relevant polymers. Of course, if A is not too large, otherwise. Okay, so this is the formal definition of polymer, and I don't have a lot of time, but okay. So now let me just mention. So now that we know what's polymers, so we know that we have this huge sum and we have the sets that we want to consider. So we know that so we have the case that both sets are large. So this is not covered by polymers. So these are the non-polymers, right? And we have the case where one is small and one is large, and the case that both are small. And in some sense, we want to show that this is the main contribution coming from these two things. But we will not show this exactly. We will actually show, we will actually calculate, we will show this, but we will actually calculate these two together and these two together. And this will give us the result we want. Maybe another thing to mention that is that when we when we think on the original model, then non-polymers just don't exist. because we don't have edges between two very large sets. But unfortunately, in our case, they do exist because we are allowed to have the edges. So we do need to handle with this thing, and it's not very trivial, but it's somehow easier from this. But we do need to keep in mind that there is another thing to deal with here. Okay, so we can just write the partition function as 2 times this because it's just symmetric, plus the non-polymers minus the thing that we counted twice. Okay, so now let's see how we can express this z prime, which is the main thing that we want to check. So we know that we have a limit on we have a bound on the size, and we can write it like this. And now we just want to split each set A to its polymers, and by just counting the possibilities, we get an upper bound. This is a maybe quite massive upper bound, but it can be written like this, which is just 2 to the 2 to the d minus 1 times the exponent of this sum of polymers. So we were able to move from summing over sets to summing over polymers that have more structure, and we know we have much more information about them, but we use this massive sum and this not really good estimation of this lower bound. Okay, so this is what we want to understand. And then, okay, so what do we have to deal with here? So we have these non-polymers that we need to deal with that don't exist in the original model. And we need to deal with this inequality. And of course, we also need to calculate this sum. This is like the main task to understand it. So the first thing to be able to get a better estimation here, instead of getting this upper bound on the polymer, this is where the cluster expansions comes into the picture. So in some sense, we can think about the cluster expansion as, instead of just doing an upper bound and with a lot of double counting, we want to do some kind of inclusion exclusion, and this is what the cluster expansion is doing, is actually allowing us to get here something much more accurate instead of this upper bound. So cluster are just sequences of polymers, but they have some but somehow they deal well with this double counting. So they have, I will define it soon, but they have this Ursel function that is doing this inclusion exclusion thing. And the way we deal with the other 2 objects or calculate them, so this is where we use the containers, the approximations, and also the entropy method. So this is basically the big picture. So let's talk perhaps a little bit about clusters. So how do we deal with this terrible? Okay, so we want to write it. So instead of writing it as an upper bound of sum of polymers, we want to have a better estimations and get it as a sum of clusters. So a cluster is just a tuple of polymers that have some connectivity relations between them. So not every tuples of polymer, and the weight of a cluster will just be the multiplicity of the weight of the polymers times this Ursel function, which depends on somehow on this connectivity structure.
I'm sorry, a what function? What's that word? I'm missing
the word is Ursel function.
How's it spelled?
You are.
Got it. Okay. E-E-L-L.
Yeah.
Okay, thank you.
Yeah, I didn't mention it here because I don't, unfortunately, I don't have time to go into all the details. I just want to say that once we've written it, instead of, so cluster expansion, so everything is finite, but I forgot to mention that this tuple is with repetition. So so maybe we're able to get a better estimation, but this sum is huge, is actually infinite. So it's not clear that it's even converges. So the first, or maybe one of the main things that we will have to do is to prove that the cluster expansion converges. And for this, we have some tools. The tools that we are using is called Kotetsky price condition. I will not write the condition here. I'll just say that it boils down to show that somehow the sum of the weights of the polymers times some function is not too large. So indeed, the objects that we are considering eventually is after doing several steps is sum of polymers times some function, but this is just to make the Kotetsky price condition happen and to show that this sum is absolutely converges. Okay, so we have so in order to bound this sum to calculate these things, so we want to bound somehow small polymers, which is an easier task, and to bound large polymer, which is maybe the main difficulty here. And for this, we want to somehow split this huge sum, but to split it in a clever way. So for splitting it, we need to use some containers and approximation. Like we want to merge together polymers that somehow behave in a similar way and split this sum using containers. And then we want to bound each splitted sum, and for this we will need the entropy methods that didn't appear in the other proofs of the independent sets in QD. They did appear in, for example, in the work of Ronan and Nunn for other graphs and models also. Okay, so maybe in the 1 minute I have left, I just want to say one more thing that we didn't take into account so far, because we talked only about the expectation, but we do want to show also higher moments, because this is how we get concentration results and other results. So for this, we had this connection between the two models. And okay, so we had this proposition, and we actually want to show that there is a similar proposition for higher moments. So there is a similar proposition for higher moments if you want to consider higher moments of the graph, but this time it will, okay, so we need some more general model to consider it. So it will be the partition function of some other models. So it will be for this model, so that the probability. So in this time, instead of sampling one independent set, we're sampling k independent set. And maybe the interesting part that they do have some interaction between them. So as you can see here, they have some dependencies. And the probability to sample one such collection will be this divided, of course, by the partition function, and we show this connection. And then, okay, so we need to do everything for everything I just explained. We need to do it actually for this model, which is a bit more complicated, which will require us, for example, one example is to define polymers in a different way. So instead of one set, we need to look at k-tuple, because the polymers will have to look different. We will need to have some a little bit more general structure on these polymers, so it will hold for higher moments. And of course, we have the weight is a little bit more involved, and so on. So we just want to keep in mind that everything we talked about, we actually need to do it for higher moments. And I'll just finish, yeah, I just stated here that, so before I stated the results only for lambda equals 1, but of course everything goes for more general lambda and the more general hardcore model. Yeah, so I think it's a good time to stop.
Thank you very much, Gal. Nice talk.
Thank you. Okay, wow, I missed so many questions.
No, it's okay. Yeah. You can ask them now. So now is the good time for questions.
This is the difficult part in online talks, right? You cannot, at least I.
So please, questions to Gal. Maybe I'll ask one question. So you analyze the hardcore model on the random subgraph of the hypercube. Can you analyze other models, maybe proper colorings on random subgraph of the hypercube?
Yeah, so no, so okay, so you're familiar a lot with this topic, so of course that hardcore model and counting independent sets is just one example of graph homomorphism, right? And we can ask if everything holds also in the more general case for other homomorphisms like colorings and stuff like this. And okay, we didn't do it, but it will probably follow similarly. It's just more involved. I mean, we just presented this type of study and the method, and wanted to show that the methods apply here and how to deal with it. But so we didn't do it, but it will probably follow in a very similar way, but just a bit more work or much more work.
Maybe one other question, can you do it on ZD instead of the hypercube? So now be fixed.
Yeah, I mean, well, again, we didn't do it, but probably it will follow.
So counting independent sets on the percolation cluster in ZD, maybe.
Yeah. So the methods will be, we think, okay, so we went through all calculations, of course, and check that everything is working, but in spirit, it should be
right.
It should be very similar.
Very good, thanks. There is a question in the chat.
Yeah, the Gaussian is a corollary. Yes, it's a corollary for the moments, not the moments as I wrote them in this presentation, because it's we need more information there, but it's a corollary of our main result about the moments if you write it in a more accurate way, is written in the paper. It is available in archive. So yeah, it's not on the slides, but it is a corollary.
And let me ask also, sorry, another question. So the thirds is an actual threshold in the model. So it's the threshold for non-concentration of the number of independent sets here. So you identify a new threshold at 2/3. So somehow.
By the way, we don't. I mean, it's a threshold of the moments. It's not necessarily a threshold on the behavior, right?
Right. So I'm trying to understand. Do you have like an intuitive idea, like that something's happening at 2/3? Can you? Do you think more is relevant at 2/3? How to understand this threshold?
Yeah, I mean, what we know is happening in 2/3 is that the moments are no longer.
The standard deviation is no longer little.
Yeah, is no longer small as we want. So this is in some sense, this is something that happens, right? If it says something more, so maybe what you're asking is actually a part of a more general question, which is what. Well, I don't know if it's exactly the same thing, but if so, we gave for this positive temperature model, we gave a lot of information. We know a lot about its structure. This is the way we prove stuff. We know about the large set and the small set, but like the way a typical independent set looks like, because this is how the proof works. But we don't have this information about our original model, or at least not for all values of P. So the only thing we have, or some of the thing, or the main thing we have, is that we just inherit the moments. And unfortunately, we don't have, for the entire range of P, we don't have structural information about our original model. We only have it about the positive temperature model. And since for some values of P, the moments are not being behave nicely anymore, then we cannot say much about this. So if someone is interested in further study, then I think understanding the behavior of a typical independent set, or how things looks like, more structural information about this model, this is still, at least for most values of P, this is still open.
Even at P equal a half, say?
Yeah.
Or for small P, even at P
Yeah.
equal a half.
Yeah, because 2/3 is above half, right? Unfortunately, we really wanted it to be below half. But unfortunately, 2/3 is above 1/2.
Right.
So we don't have a structural information there, at least not for the random model. We do have for the positive temperature model, but not for the random model.
Sure. That's
I'm
very
sorry, in the last corollary, what is lambda? In the left-hand side, there is no lambda, but in the right-hand side, there is lambda. What is lambda?
Right? I forgot.
Last column.
Yeah,
The
it
last.
should be the, it shouldn't be I should have written here Z QDP lambda. So the partition function of the, you're right, example, I'm sorry.
Thank you. Mhm.
Yeah. And yeah, okay, you're right.
okay. If there are no further questions, let's thank Gal again.
Thank you very much.
Thank you for coming.
Yeah, it's a pleasure to be in Israel, always.
And again in 2 weeks, and I'll send an announcement.